All right, rolling right along here in section 13.6, we'll next look at question number 6. Here we have the function f of xy is x cubed minus 2xy plus 1/2 y squared. And in part A, it says to find the direction or directions u and the value or values of the derivative of our function f at the point 1, 1 in the direction of u, for which, and then we have some various conditions here. So the first condition here is that we want the directional derivative here to be greatest. Okay, and what we know from our previous video on the gradient, right, that's going to occur when we move in the direction of the gradient itself, right? So let's go ahead and compute the gradient up here. And so this is going to be our vector whose components are these partial derivatives. So computing those, well, the x derivative would be 3x squared minus 2y, and the y derivative would be minus 2x plus y. So then evaluating this thing at the point 1, 1 will give us the vector 1, negative 1. Okay, now the way this notation is set up, u here, since it's acting as the subscript in the directional derivative, u really is a unit vector, okay? And I see that the gradient is not a unit vector, right? Its magnitude would be the square root of 2, right? Because 1 squared and 1 squared, there is 2. So what I'm going to do here for my answer to part 1 is I'm going to go ahead and say move in the unit vector in the direction of the gradient at 1, 1. So this would be 1 over root 2, comma, negative 1 over root 2. So I'm just dividing the gradient by its magnitude. And then we also prove that the maximum rate of increase is simply equal to the magnitude of the gradient evaluated at the point, which is equal to the square root of 2. Alright, so these would be our answers for this first part. And then for the second part, when is the directional derivative smallest? Well, in question 5, we argued why we should just, in that case, move in the direction opposite the gradient. So here we're just going to do the opposite of this vector. So that'd be minus 1 over root 2, 1 over root 2. And we also, in that video, showed that the maximum rate of decrease, right, for our function will be the opposite of the magnitude of our gradient. So this would be minus root 2. Okay, so here are the answers for the first two parts. And so then let's go ahead and check the other two out over here. So in 3, we're looking at where the directional derivative will equal 0. Okay, so let's go ahead and draw a little picture up here. So let's say here's our point P, and here is the level curve. And we know that the gradient points in the direction here orthogonal to this level curve. Okay, so if I want to have a 0 directional derivative, what I ultimately am saying graphically is that I want 0 change in altitude. So in other words, I want to move along my level curve, right? I want to move in the direction tangent to this level curve. All right, so the idea there is, look, if this vector, the gradient, is 1, negative 1, what would be a vector that would be, say, perpendicular to it? Well, what I can do there is just say, right, what's a vector whose dot product with the gradient is 0? And if I change, say, the sign of just the first component, right, now these two vectors will have a dot product of 0. I'm going to get -1 plus 1, that's 0. But, right, is that the only vector that would do that? No. I mean, aside from positive scalar multiples, we could also, though, move in the direction opposite this vector -1, -1. So in other words, we could also move in this direction 1, 1. So if we do that, right, then we're moving tangent to this level curve, and that would give us a 0 directional derivative. And again, since u here is going to be a unit vector, I'll go ahead and just divide these two vectors by their magnitude. So we're looking at the vectors plus or minus 1 over root 2, okay? And then for the second component, those are going to be the same, right? Plus or minus 1 over root 2. All right. So I can move in either one of those, in the direction of either one of those unit vectors. Now, for the fourth part, right, we want the directional derivative to be 1. Okay, so what I'll do here, I'll just draw that similar picture. Here's P and the level curve that passes through P, and here is our gradient. And then we're now going to choose some unit vector, u, and I'll go ahead and just give this a name. I'll say it's, say, u1 and u2. And we want the directional derivative to come out to equal 1. Alright, so how do we compute this directional derivative? Well, it's the gradient vector evaluated at our point dotted with this unit vector we're looking for, and that has to come out to be 1. Alright, so that's saying if I take the dot product of, well, our gradient, which was 1, -1, dotted with this unknown vector, which is u1, u2, this has to equal 1. Now taking that dot product, I'm going to get u1 minus u2, that's going to have to come out to equal 1. Okay, so doesn't seem like quite enough info to uniquely solve for u1 and u2. However, there is a condition on this vector u we haven't made use of, right? The thing to remember, I'll make a little note here, is that the magnitude of this vector u is 1, right? It's a unit vector. So put it another way, if I take the sum of the squares of u1 and u2, that must equal 1. So now I have two conditions, and I can go ahead and say, alright, I'm gonna, in this equation, say that u1 is equal to u2 plus 1, and now replace u1 here with the u2 plus 1. Okay, and so what are we going to get there? Kind of surprisingly complicated, right? So we're going to get u2 plus 1 quantity squared plus u2 squared is equal to 1. The upshot here is that we're at least getting now an equation with just one unknown. So expanding, I'll get u2 squared and another u2 squared, so 2u2 squared plus 2u2. And notice I'm going to get a plus 1 here from the binomial expansion, but then I also have a 1 over there, and those 1s are going to cancel out, and so in fact this would just equal 0. So continuing over here, I'll go ahead and factor out that 2u2, and I'd be left with u2 plus 1 is equal to 0. So in other words, u2 is either going to equal 0 or -1. And so then what can u1 equal? Well, if u2 was 0, then u1 would have to equal 1. And if u2 were -1, then u1 would be 0, okay? So when all is said and done, putting that all together, what are our direction vectors? Well, if I took u1 to be 1 and u2 to be 0, that would tell me the vector 1, 0. Or we're saying that if I took u1 to be 0 and u2 to be -1, right, this could be 0, -1. Notice these are both unit vectors, so we're okay there. And we're saying, yeah, either one of those directions would be such that if we walked in that direction, the steepness of our surface, right, would be 1. So a little more work there algebraically, but yeah, there you go. The last part, fortunately, is pretty quick. It just says, is there a direction u for which the directional derivative is equal to 3? Well, the answer there is no, there is not. And why is that? Well, remember back here in A part 1, we found that the directional derivative, right, the max of the directional derivative, that's just the magnitude of the gradient vector, and that is the square root of 2. And that's, of course, less than 3. So we can never achieve a value of 3 for that directional derivative, and that's going to do it. All right, I'll see you in the next video.